Okay, let's get started. So, so we are learning about the hardware part now. So as I mentioned, so we complete the instructions and architecture. So in chapter 2, we learned about the ISA, so instructions. Okay, so so actually, in order to design a processor, then we need to define instructions, right? And then these instructions are executed by a processor. And then if a processor execute instructions, then the processor generate the output. Outputs defined by ISA, so instruction set architecture. So actually, in order to generate the output of instructions, so we require hardware, right? And then actually, so if you read the instruction set architecture document, then you can find that ISA includes many arithmetic and logical instructions. So arithmetic means that adder, so add, subtract, multiply, and divide. And then also logical instructions means that it's the and or, so it's a logical operation, right? So, so in order to support these instructions, our processor needs to include hardware, hardware components that can generate the outputs of instructions. So we are learning about these arithmetic units. Okay, so we learned about the adder and subtractor. So actually, so we will not learn about the detailed architecture or detailed structure of these arithmetic units. So because we are learning about the ab- the some abstraction level. So this is the microarchitecture abstraction level in the computer systems. But so for the detailed architecture or detailed structure of these arithmetic units are handled by some different abstraction level, such as the digital design and then some RTL, so digital design, right? Or so logic design. Okay, so so you can just understand how these arithmetic operations are performed in the processor. Also, I mentioned that. So I mentioned that. So hardware learns in the real world, right? So which means that actually the hardware just takes time. So 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 if you took the digital logic design course, then actually so I believe you learned how the combinational logic or some hardware component works. Okay, so which means that if input is given, so like the input signals, such as these input signals are digital signals, and then the output signals, so output data are generated, but after delay, right? So delta t. So this delay, so delay of a hardware component is determined by the complexity of hardware. So which means if a hardware is complex, then it will take long time. But if the hardware is simple, then it will take a short time, right? So actually, so we need to use, so we need to design a simpler hardware. So that's the reason. So which means with a simpler hardware, so we can increase the performance because this delta t, the delay can be reduced, right? Also, we can reduce the cost of hardware. If the hardware structure is simple, then this hardware will consume lower power also. So we can just reduce the cost. Okay. So we can also reduce the manufacturing cost because this hardware will not occupy the large area. So we just a small area. So small area. Okay. So And so we learned about the adder. So adder is very simple. So as I mentioned, okay, so adder is just this is the integer adder. Then the integer adder is very simple, right? And then we can just implement the subtractor using adder, right? So we can just change the sign of the one of the operand of this subtractor, right? So we can just apply the sign inversion, okay, sign inversion method of the two's complement number, right? And then multiplication. So multiplication is more complex. It's more complex than adder. So this is because I explained that actually for multiplication, so we need to generate multiple partial products, right? And then we need to add. We need to add the multiple partial products. Okay, so so when you learned about the multiplication, so the multiplication is uh, it's more difficult, right? More difficult than addition, right? So that's true. That's also true for the hardware design. So multiplication is more complex. It's more difficult. Division. So you can just understand how the binary division is performed. So it's the same. It's the same to the decimal division, right? Okay, but actually the division includes the comparison, and then based on the comparison, then the the hardware may perform subtraction or not. Okay, so for example, if the dividend, so actually I do not have so this pen. So where is the okay. Oh, it does not work. Sorry. Okay, so I try to use the can use. Okay, so I may use the okay, so the in the division, the dividend can be subtracted by divisor, but if the part of dividend, so part of dividend is this one, right? Okay, so it is that this part of dividend is larger than the divisor, then we need to perform subtraction. And then the quotient becomes 1, right? Like this. But if the dividend is smaller than divisor, then so it becomes 0. But we do not need to perform subtraction. So you need to understand that in the division includes the comparison, and then based on the comparison, then we may perform the subtraction or not. And then this operation is not good for the hardware design. So 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 actually, if a processor does not include divider hardware, then we can implement this division using integer unit, right? So we can just so the baseline RISC-V processor. So baseline RISC-V ISA is integer ISA. So it just includes integer instructions. But in a normal program, so in a usual program, we can use division. Then how this division works in this very basic RISC-V processor. So actually, we can make a division function, and then this division function can be implemented using integer instructions like integer subtraction and if else, right? The branch instructions, right? So a branch instruction is not good for the performance of a system, right? So usually, so we will learn the reason in the later, but usually the branch instruction is not good. So it's not good for the performance. Okay, so and then the division includes the comparison, right? And then based on the comparison condition, then subtraction can be performed. So it's not good. The performance, actually the performance of a division is lower. It's lower than the, it's lower than the multiplication actually. So, so you, so we may design best division. So, but it's, so as I mentioned, we will not learn about the how to design the detailed the hardware components. So this is the abstract this is the some levels of the hardware design or digital design. Okay, but you know, so we can just design some different type of dividers. Okay, so RISC-V supports the division instruction, but in order to use this division, then we need to include the M. Okay, so M means the multiplication. So M extension, right? So I extension. So you know, so we are learning about the RISC-V baseline integer instruction set, right? It's called I extension. But this I extension does not include the multiplication or division. Okay, but if we include the multiplication, so you know in the lab, so actually when we compile the RISC-V compiler, so compile the build, when we build a RISC-V compiler, so you can just observe that. So I just added the M extension, right? So in order to support the multiplication, right? But if I just use I extension only, then RISC-V just includes the in basic integer instructions. So except the multiplication and division. So actually these multiplication and divisions are implemented using basic add and subtraction instruction, right? Okay, so RISC-V with the M extension, the RISC-V supports the divide and remainder. So these instructions. So div instruction just generate the signed quotient. So it performs a signed division and then it generates quotient. Okay, and then REM. So REM instruction just generate the remainder. Okay, we can also use some unsigned divide and unsigned remainder. Okay. So now let's learn about the floating point structure. So floating point format. So what is floating point? So floating point is the non-integer number. So in Korean, it's called the 실수, right? It's a real number, right? And then integer is a 정수, right? So integer is just 정수. So which means that after the point, there is no number after the point, but we can use the real number in our real life, right? So actually, a processor needs to support floating point data. Okay, so floating point data, and then you know recently the AI applications. So AI applications are very popular, but the baseline AI applications just handle floating point numbers, okay? Floating point data. So, and then, you know, so actually in real life, the real number is more complex, right? It's the complex means that actually the real number can represent so many different numbers, okay? But we know the real number is actually it's a more complex than integer numbers, right? It's the same. It's the same to the computer hardware. Floating point format, the floating point numbers, in order to represent floating point numbers, so we need to use the more complex format, okay? More complex data format, right? And then we will learn how how these floating point numbers can be represented in the processor. Okay, so this is the real notation. So you can find the here. So some numbers here. So actually, this is the some scientific notation. So in a decimal number, in order to represent the real number in a scientific format, then we can write the numbers like this. So it's a minus 2.34 multiplied by 10 to the power of 56. Okay. So these numbers include some numbers. Okay. So these numbers are called fraction, and then this we are handling decimal numbers, so we can just represent some very large numbers using the power of 10, right? So you can find these numbers, the power of 10. So this number is called the exponent. Okay, so real numbers in a scientific notation. So we can represent real numbers using some fractions, and then also these numbers can be called the mantissa, and then using the power of 10 using the exponent. Okay. So this is the decimal number. Then how can we represent the binary number, binary real number, binary floating point number. So in a decimal number, the base is the 10, right? So in a binary number, the base is 2, right? So we can use the power of 2, okay? And then we can also use the exponent numbers for the power of 2. And so like these numbers, so we can also use the fractions, okay? But so actually, if you see these numbers, the first number, this number is the normalized number. So normalized means that, so actually the number of digit of the left side of this point is just 1 digit. So normalized in a decimal number, normalized means, so actually in the left side of this dot is a point is just 1. So we have only 1 digit. So we can just apply the same notation to the binary number. But actually in a binary, this digit, if we just have a certain number in this digit, okay, then you can find that actually this number is always 1, right? Because so this is normalized, and then normalized means that actually this left side of this point is just 1 digit, but it needs to have 1. Okay, so this number is always 1. So we can just represent the remaining fractions, okay, like x. And then also in order to represent the real number, so we need to represent the sign, okay, plus and minus. So what data are required? So in order to represent floating point numbers with a binary format, we require sign bit, right? We require fraction part, okay? These numbers. Also, we require exponent part, okay? So actually we can combine these numbers like the sign bit and then fraction part and the exponent part to represent the floating point number. So in C we can use the float data type. So float means it's a floating point, and then double data type. The size of this float data type is the 4 byte, right? It's a 32 bit, and then double double means the size of double is 8 byte. It's a 64 bit. Okay. So it means actually, the C is tightly coupled with the hardware design, right? So actually there are two standards, two methods to for representing floating point numbers. So we can use the single precision and double precision. Okay. So single precision, the float data type. This float data type is matched with the single precision floating point type. So it means we can use 4-byte data, okay, to represent the float data type. So this is the single precision. For the double precision, so it's 8-byte data. So we can also, so it's the same actually, right? So double data type, so it's a double precision. So in order to you represent the double precision floating point number, so we can use 8-byte of data. Okay, so let's see. So floating point number, floating point number representation is defined by IEEE standard. Okay, then okay, there are two representations, like a single precision is, as I mentioned, so it uses 32-bit data, and then double precision, so it uses 64-bit data. So this is the single, no, float. This is the float data type, so single precision, and then double data type in C represent the double precision floating point number. Okay. Okay. So then let's see how we can represent floating point numbers. So as I mentioned, we require the three different type of data. The first, the sign bit, the plus and minus, and then we need to use fraction part number, and then exponent number. So you can find the format of this floating point number representation. So in order to represent the sign bit, the sign just have the two cases like plus and minus. So we just require 1 bit of data. So this is the sign bit. And then for the exponent part, so you can find that exponent part is the here, right? So to the number, the power of 2. So in a single precision floating point type, so we use the 8-bit exponent field. So which means we can just use 8-bit numbers to represent this exponent part. Okay. And then for the double precision, then we can use the 11-bit data for representing exponent numbers. And then for the fraction part, so you can find the fraction part here. Okay, so it's a 1.xxxx, right? So in order to represent this fraction part, so for the single precision floating point number, so we can use the 23-bit data. Okay, and then for the double precision, so we can use the 52-bit data for representing this fraction part. So with these three fields, like a sign field, exponent field, and fraction field, so we can represent a number using like this. So this is the floating point representation. So what can you? So I think I did. Okay. So I believe I need to use. Oh, it's better, right? 자동이야. Okay, okay. So So as I mentioned, we can represent the floating point like plus minus is a sign bit and then 1 point xxx. So this is the fraction part. And then multiply by 2 to the power of exponent. Okay. But so actually this is the standard. So which means that you can just memorize. Okay. So actually we can use these numbers for this fraction part, right? But exponent part is so a little bit different. Okay. So you know for this number, we can use the plus number and minus number, right? So think about this. So in a decimal number, we can write the number for the exponent part like the 10 plus power of 2 or 10 to the power of minus 2. So we can use the plus number and minus number for the exponent part. And then we learned that in the integer data type, so we can use the two's complement number. Two's complement number for representing plus and minus numbers, right? But in the floating point number, the rule is different. So actually, this number, so we can use the plus and minus number, but we do not use two's complement number. Okay, so you need to understand this. So actually, the this exponent part, actually the real number for this exponent part is the exponent minus bias. Okay, so it's a little bit different. Okay, so and then for the single precision data, the bias is 127, and then in the double precision data, the bias is the 10,023. Okay, so it means if the real exponent is 0, right? It's a 10 to the power of 0, so which is actually, this is 1, right? But in order to represent the exponent number 0, then we need to use the 127, right? Right? So because the bias is 127, so minus bias is 0. So just to remember that, you know, so this floating point number format. So for the exponent part, so we can use the plus and minus numbers, but the rule is different. Okay, so rule is the exponent part minus bias. So bias is the 127. Okay, and then for the single precision, and then for the double precision, this is the 1023. Okay, so you can just observe that it's a single precision. The exponent bit is the 8 bit. So what is the 127? 127 is the 2 to the 7 minus 1. Okay, so you can find that this is around the half. The half of the 8-bit numbers. Okay, it's the same. So 10,023. So this is the 2 to the power of 10 minus 1. Okay, so it's around the half of this 11-bit positive numbers. Okay, so and then so in the floating point numbers, the exponent all zeros and the exponent all ones are reserved. So for the normal number representation, we do not use the all zeros or all ones for the exponent part. So what is the smallest value? So what is the smallest value of this single precision? So it means the exponent part is the 1. Then what is the real exponent number? The real exponent number is the 1 minus 127. So this is the bias. So so the exponent number is the minus 126, right? And then, so the fraction part is the 1.xxxx. So what is the smallest number? All fraction part is 0, right? So the fraction part is all zeros, and then exponent is the 1. The real bias is the real exponent is the minus 126. So this is the smallest value. Okay. So this is the smallest value, and then in decimal number is around the 10 to the power of 38. The largest value, because the all ones are reserved, so it is used for representing special numbers, right? So the largest exponent is the 11110. Okay, so actual exponent is the 127, and then all fractions are 1. Okay, so it's around the 2.0. So it's the 1.111111. Okay, so it means, so this is the 1, right? Binary number. And then what is this number? This is the 2 over 1. This is the 4 over 1. This is the 8, 1 over 8, right? So this is 2, nearly 2, right? So it's a it's a mathematics, right? So thus this is the largest number in a single precision floating point. Okay, so around this number in decimal number. So for the double precision, actually for the double precision, so you can find that the format is different. For the exponent part, the double precision, we can use the 11-bit. And then for the fraction part, we can use the 52-bit, right? So we can just apply the same rule, okay? For the smallest value, so 1, okay? And then you can find that for the double precision, so this is the smallest value. The smallest value that can be represented using double precision floating point format. This is the largest value that can be represented using the double precision format. Okay. So let's see some relative precision. So the precision means that is we use the 1.xxx. So this is the fraction part. So precision means that this is the smallest number that can be using the smallest value of this fraction part. Okay. So in a single precision, this is the approximately 2 to the power of minus 23. It's around the 6 decimal point, right? So because we need to use the binary number for representing floating point number. So we can think that floating point number representation, we can use the very large, very many bits, the many bits for representing this fraction part. But actually, in decimal number, the precision is just the 6 decimal point. Okay, so because so this is the equation, right? So it's because actually decimal number is like 1.2345. So this is the 1 over 10. This is the 100, 1 over 100, and then blah blah blah. But actually, in a binary number, this number is the 1.1111. So this is the 1 over 2. This is the 1 over 4, 1 over 8. So that's why, even though we use the many bits for representing the fraction part, but the precision is actually It's not high, it's low. So using the single precision floating point number, so we can represent around the 6 decimal point, and then for the double precision, we can represent around the 16 decimal point. Okay. So this is the example. Then how can we convert the minus 0.75 to the floating point number? So, the sign bit is minus. So if the if the number is the negative number, then sign bit is just 1. And then if we can check the magnitude of this number. So what is this is the 3 over 4. So this is the 1 over 2 plus 1 over 4. So actually this is the 0 point. So in a floating point number, this number is the 0.11, right? Do you understand? But in a floating point number, the fraction part is the normalized. So which means it should be represented like the 1.x x x blah blah blah. So actually this number is the 1.11000 multiplied by 2 to the power of minus 1. Right. So the fraction part is the 1000, right? And then so this is the exponent part. So exponent is the exponent number is the exponent minus bias, so 127. So this is the minus 1. So exponent needs to be 128, right? 126. 126. So this is the fraction part. 1000, as I mentioned. So this is the fraction part. And the exponent part is the 126 in the single precision. So it's the 0.11110. Okay, so that's how we can convert the floating point number. And then actually we can also represent the decimal numbers using the floating point format, but it's easier, right? So we can just apply the floating point standard. So this is the example, like the 1 0 and then 0 1 0 0 0 0. So based on the floating point representation rule, so this is the rule, right? The first bit is the sign bit, right? So sign bit is 1, right? Because the first bit, the MSB is the 1. So it's the minus number. And then fraction part. So this is the fraction part, right? So the fraction part is the 0 1 0 0 0, right? So it's the 1 0 0 1 0 0 0, right? And then exponent part is the 1 0 0 0 1. So this is the 129. And then the bias is 127, single precision. So actual exponent is the 129, 27, 2. So it's the 2 to the power of 2. And then minus 1. It's the sign bit is 1. So this is the calculation. So we can calculate the equivalent decimal number from the single precision floating point format. Okay. Then I mentioned that, so if all exponents are zeros or all exponents are ones, then these cases are used for representing special numbers, so not normal numbers. So this I mentioned this is the special numbers. So these numbers are the normal numbers, right? Not normal. So it's the normal numbers. Okay. So if the floating exponent parts are all zero, and then if the exponent are all ones, then we can use this format for representing the normal numbers. So first case is the exponent are all zeros. Okay. So actually, if we just apply the same rule or same floating point representation, if the all exponent numbers are zeros, then it represents the 1 minus bias 127, right? So this is the 2 to the power of 127, right? But actually, so you can observe that this number is the very small number, right? It has very small values, but we for this case we apply the different rule. So what is different? What is different compared to the normal floating point representation? So this part is different, right? So in the normal part, it was the 1 plus fraction, right? But in the denominator number, if the whole number is the zeros, then this is the 0 plus fraction. Also, this is different. Okay, so instead of the minus bias, it is the minus bias plus 1. Okay, so actually, uh, we use, but if the exponent all exponents are zeros, then we need to use the different representation. Okay, like this. So why do we need to use the some different rule if the exponent all exponents are zeros? It is because actually with the normal floating point representation rule, we cannot represent zero. So that's the reason. Why? Because, if we just apply normal floating point representation, this is the 1 point fraction multiplied by 2 to the power of exponent minus bias. Okay, so in order to represent the zero, so we can just use the very small number, right? Which means all fractions are zero, right? And then exponent is also zero. Then what's the very small number? This is the 1.0 multiplied by 2 to the power of 127 in a single precision floating point number. But this number is not zero, right? Do you understand? So if we apply the same rule, so the same floating point representation, then we cannot represent zero. So that's the problem. So if the exponent is all zeros, we can apply the different rule. So, in a different rule, this is zero, right? So it becomes the 0.0 and then multiplied by 2 to the power of 126. This number is zero, right? So that's why if the all exponents are zeros, then we use different rule. Okay, so that's the reason. Okay, so you can just observe that it means then there are two representations for 0. Why? Because floating point number includes the sign bit. So we can use 1, 0, 0, 0. This is also minus 0. And then 0, 0, 0, 0 in floating point number. This is 0. Right? There are two representations, plus 0 and minus 0. But we already know plus 0 is minus 0 is equal to minus 0. So, but actually, so there are two representations, okay, by the floating point rules, okay? And then all exponents are ones. So if the exponent number is very large, so then we can just assume that, oh, this is a very large number, right? So if the all exponents are 1, 1, 1, 1, so it's a very large number, and minus bias, so this is also very large. But, floating point number, floating point format, we use this all ones for representing special cases, like the infinity or NaN, not a number. So if you use Microsoft Excel, then sometimes you can observe, oh, this is not a number, right? NaN. Okay, so actually, so in a computer system, then we sometimes the hardware needs to detect some not a number. Okay, so it's the abnormal cases. Okay. Also, sometimes the hardware may represent the very large number cases. It's infinity. Okay. So in order to represent the infinity, then we can just set, oh, 환경이 안 좋습니다. All exponent are 1, and then all fractions are 0, then this represents the infinite number, okay, like this. So, and then also, we can just use the sign bit, right? So if the sign bit is 0, then it's the positive number. So we can just represent the plus infinite, okay? And then if the sign bit is minus the 1, then it represents the minus infinite, okay? And then the another case is the exponents are all ones, and then fraction part is not 0, okay? And it represents the not a number, okay? Not a number. So it's a NaN, okay? So it is used for representing some abnormal cases, right? So this is the rule. So as I mentioned, so this is the standard. Okay, so just the definition. So you can just memorize this definition. Okay, so and then you can just understand how the floating point is represented. Okay, and then sometimes this is important. It is because, so actually the AI applications, so I mentioned that AI applications usually handle floating point numbers. So it means actually the floating point format determines the precision of AI applications, right? So we just mentioned the the precision of the floating point number. So this is some smallest value that can be represented using this format, the floating point format. And then this precision can decide the accuracy. accuracy of AI applications. Okay, so that's why the floating point. So you need to understand this floating point format. Okay, so and then so actually the AI. So in order to understand the AI applications, you need to understand the uh, basic basic baselines, the fundamental baselines of some mathematics or statistics, right? And then, as I mentioned, the precision of data may decide some accuracy of this AI applications. So, and then we need to use these numbers, right? So so as I mentioned, our applications usually handle the number data, right? So that's why the precision or the representation rule is critical. It's a critical recently. It's a more critical recently because the the AI applications are very popular, and then based on the precision, the, the performance or accuracy of AI applications can be changed. Okay, so then let's let's discuss how the floating point arithmetic is performed in a processor. So how can we calculate the floating point number in a decimal number systems? This is the example, right? So this is the example. The 9.999 multiplied by 10 to the power of 1 plus 1.6. So this is the example. First, what we need to do is the align decimal point. So you can find that, oh, this number is composed of a mantissa, right? The 9.9, and then multiplied by exponent part. But in order to perform the addition, then we need to align this decimal point part, right? It means the exponent part, right? Obviously, right? So this is the example. We just adjust the decimal point of this number. Okay, and then after that, we can just add the mantissa part, the significant part, right? So this is the result, and then is to be normalized, right? So, and sometimes we can just round and round up or round down this significant part, the mantissa part. Same. Binary number, binary floating point number, the required steps for this addition are the same. Firstly, we need to align binary points, right? And then at the fraction part, okay, so at the significant, and then we can just calculate the significant part. And then we need to normalize in order to represent the real number using the floating point number format. So we need to normalize this binary number. So it becomes the 1.00 and then multiply by 2 to the power of -4. Then it can be, this is the final result. So for the floating point addition, we need to perform these 4 steps, right? So why did I explain this? Hardware, in hardware also needs to perform the same steps, right? And then, this addition, the floating point addition is obviously more complex, more complex than integer addition. And then it means the hardware is more complex. It means hardware will take longer time. Okay. So in chapter 4, we will learn about the hardware architecture, the hardware implementation of a processor, and which means you need to understand the delay of hardware, right? So it is because the delay of hardware determines the influences the performance, right? Also, it influences the cost. Okay, floating point. So unlike the integer arithmetic units, the floating point arithmetic units are more complex, and then delay is longer. Okay, so we need to apply some different types of hardware for the floating point engine. Okay, I hope you can understand this. So it's a more complex, as I mentioned. Okay, and then you can just find this one. So floating point adder usually takes several cycles. So what does that mean? Several cycles. Okay. So it means so for the integer adder, and then I mentioned that the hardware of this integer adder is very simple, right? So it means that the delta t, the delay is also very low. Okay. So and then actually this delay, the delay of hardware determines the clock period. Okay. So so I will explain later in chapter 4, but actually we can just implement the pipeline, the hardware pipeline hardware like this is a combination logic, and then this is the pipeline registers such as the D flip-flop. And then this delay, the delay of this combinational logic part is as the TC, because the TC needs to be larger than the delay of this combinational logic, right? So that's this is what we learned in the digital logic design course, right? So and then we learned that actually the execution time TEXE. So what is this one? Instruction count multiplied by CPI multiplied by TC, right? So you need to memorize this, right? So actually the hardware complexity determines the TC, right? So integer addition, integer adder is simple. So we can just reduce this delta T. But floating point adder is more complex. So delta T, the delay of this floating point adder is very high. So in this case, in order to reduce this delta T that determines the TC, the clock period, we can apply the pipelining. Okay, so you can also find the pipeline here, but unfortunately, we did not learn about the pipelining, because we will learn about the pipelining in chapter 4, right? So, but just assume that, yes. So, but I want to explain so you can understand that the hardware is complex. So it will take longer time. Then it can be pipelined. Okay. So that's why, so in chapter 3, so we are learning about some some hardware components of the arithmetic units. Okay, so this is the floating point addition. So as you can see, this addition is more complex. Actually, you know, this addition just implement the required steps. the required steps for floating point addition, right? So, and then how about the multiplication? So these are the required steps for the decimal multiplication, decimal floating point multiplication. So multiplication is a little bit different, right? But I believe you can understand. The firstly, we can add the exponent part. So this is the multiplication. And then the significant, the mantisars needs to be multiplied, right? So, the significant are multiplied. So we can just apply the addition, and then the significant, the mantisar part are multiplied. Okay. So this is the final result, but enough for the scientific notation, we need to normalize. Okay. So, and then sometimes we can just apply round up or round down. Okay. And sign bit. The sign bit is just determined. Okay. So, but the sign can be determined in an easy way, right? So it's very easy, right? The plus multiply plus is plus, minus multiply by minus is a plus, right? And then plus multiply minus is a minus. So we can just determine the sign bit or the final result like this. Finally, same. Okay, so we can apply the same steps for the binary multiplication. So this is the example. Okay, so it's a floating point number example. Its exponents are just added, and then we can just multiply significant. Okay, then we apply normalization. Okay, normalize result, and then determines the sign. So these are record steps, and then actually the multiplication can be just apply the similar steps for the floating point adder. So usually the complexity of floating point addition and the complexity of floating point multiplication is similar. Okay, so in integer, the integer arithmetic integer addition is very, very simple, right? So, but we learned that integer multiplication is complex. Integer division is more complex. But for the floating point numbers, the complexity of arithmetics is similar. So complexity of floating point addition is similar to the complexity of floating point multiplication. Okay, so you can find the can be hyperlined. Okay, so because it takes several cycles. Okay, so in this course, so we are learning about the integer instructions. Okay, but actually general purpose CPUs, actually normal CPUs support the floating point numbers, okay, floating point arithmetics, right? Because in C we frequently use floating point numbers, right? So usually normal processors support the floating point numbers, but we just learned about the integer instructions, and then integer instructions just access general purpose register like the X0 to X31. Okay. But in the processor, floating point numbers are stored in the floating point register, like from F0 to F31. So it means the register files are separated. Do you understand? integer type data are stored in this general purpose registers. So integer type registers, like from x0 to x31 in RISC-V. Floating point numbers are stored in the floating point registers, like F0 to F31. It's just separated. Okay. So registers are separated. Also, so in order to support the floating point numbers, the RISC-V supports the additional floating point instructions. Okay. So also you can find the FP load and FP store, like FLW, FLD, or FSW, and FSD. Then what is different? What is different with the normal load or store instruction? The difference is that I mentioned that the floating point, the registers are separated, right? So for the load instruction, the destination is different. So if we use the FLW, like F load word, then destination is the floating point registers. F store, FSW, then source register becomes the floating point. Okay. So just to remember that in a processor, so normal processor, integer registers are separate from the floating point registers. So floating point registers are separated. Okay. So these are floating point instructions in RISC-V. So you can find fadd, fmol, fdiv, fsquirt, okay, and then so you can find the postfix here .s or .d. So .s means it's a single precision, and then .d represent the double precision floating point operation. Okay. So this is the example code. So you can find some example code here. Okay. And then so actually we can just apply some standard, the floating point standard to the hardware, but some standards can be just ignored because so actually this IEEE standard 754 defines so many part of the floating point representation, but we can just trade off some hardware design for some more uh, the precision or some choices. Okay, some hardware design choices. Okay. Okay. So this is the floating point numbers, and then we will skip the subword parallelism. Okay. Okay. So and then this is some peoples. Okay. And then so So we learned that so sometimes we can just apply the shift operation. So shift operation for replacing the multiplication or division. So actually we can use the right shift operation for implementing some power of 2 division, right? But this the right shift is can be maybe just applied for the unsigned integer. So for some correct result. So this is the example. So -5 divided by 4. Actually, the correct result is 1, right? Because the correct result is the 1. But if we just apply the right shift by 2, because it is divided by 4, so it is equivalent to the right shift by 2, right? But you can find that the result is -2. So result can be different. So when you apply the right shift, then actually the number needs to be unsigned integer. Okay. If the target number is the minus number, then the result may be incorrect. Okay. Also, So this is the some some interesting part. So associativity. So this is the x, y, and z. Okay, and then we can just apply x plus y plus z, and then we already actually we know that this is equivalent to x plus y plus z because this is the associativity in the mathematics. Okay, associativity in addition, right? Actually, in real world, this is the same. But what's the problem? We can just observe the exponent part is very large. It's a very large number. What's the problem? Actually, these large numbers need to be represented in floating point format, right? And then the precision, there can be precision problem. So let's see the example. So if we just perform the x plus y first, this result is the 0 by the floating point operation, and then plus 1, then the final result is 1, right? How about this one? If we just first apply y plus z, problem is that, this is the very large number plus very small number, so 1.0, and then the result cannot be represented using the floating point format correctly. So the result is the 1.5, so it's rounded down, okay? So very small number is rounded down, and then plus minus 1.5 plus 1.5, very large number is the 0. The problem is the final result can be different. It is the effect of floating point representation. It's a precision problem. Okay, so this is the example. So I also mentioned the AI application. So sometimes because of the precision problem, the accuracy. So this is the example. The accuracy can be influenced. Okay, so sometimes the result can be different. Okay. Okay, so this is the end of the chapter 3. Okay, so and then the important part is the floating point representation. Okay, and then also you need to understand how the hardware is implemented. Okay, you need to understand the complexity and then some delay of the hardware. Okay, okay, the midterm will cover until the chapter 3, as I mentioned. Okay, then unfortunately, we will have classes, the next class. Okay, so see you in the next class on Thursday. Any question? Okay, thank you for your attention.